rephrase the question that, is there any AI task that deep learning cannot do?
Pretty much all of them, except a tiny number of exceptions. I mean, the ones that deep learning can do are the ones for which we have tons of data that we can train supervised, and for which it doesn't require a ridiculously large amount of data. So any task that requires a little bit of common sense about how the world works, deep learning won't work because we don't know how to train machines to acquire common sense. So a good example of this is something called Winograd schemas. So an example of this is you form a sentence with a pronoun, and the noun that the pronoun refers to depends on your knowledge of the world. So for example, if you say the trophy doesn't fit in the suitcase because it's too small, then you know that the it refers to the suitcase. If you say the trophy doesn't fit in the suitcase because it's too large, then you know it's the trophy. So because you know that the kind of physical role of those objects, and there is the best systems as of this week do like 70% correct on this, maybe a little more. The latest GPT-2 thing from OpenAI, I think, is a little above 70%, which is not that great. Like humans do above 95, I think. Yes.
Can I follow up on that? Because I'm actually quite interested in, I mean, there are huge, particularly in science, there are huge data sets. So even in that class of problems where huge data sets are available, are there examples that are already kind of known not to be solvable with deep learning? I know there have been many attempts in the biomedical realm, for instance, or just it's too complicated.
Multiplying numbers.
You're talking about practical problems? Well, I think that every problem that has combinatorial nature cannot be solved by deep learning, simply because even if you have a very large data set, it will not be combinatorially exponentially large. Okay, so where deep networks succeed is mainly problems where the structure is not that complicated. So for example, in computer vision, what you see in the image, okay, there is a lot of structure and you need to memorize a lot of things and to really grasp what's going on, but there is no combinatorial structure. But if you take a very complicated story where things can very, very quickly be complicated and the branching is large and there are many, many options that can stem from the same thing, then deep learning will struggle unless you force them into some structure.
Yeah, I mean, I think maybe one comment is where I think this kind of conversation about like what can deep learning do or what can not deep learning do, and I guess Jan is frequently a party to one such epic debate on Twitter, which is maybe not the best medium for it, with Gary Marcus. But
Let's stop arguing with Gary.
I won't go too deep into that. But I think one point is that sometimes the question that it ends up sort of collapsing onto is not really is really just one of sort of semantics of what do we mean by deep learning, because there's this one consideration of like what is the parametric form of a model, and that's not the only kind of form. So if by deep learning we mean like the standard supervised approach of I collect a bunch of data points, I fit a function based on these points that, like there's some things that just the standard supervised learning in a framework altogether doesn't account for. And among these are whatever is required to generalize, not generalize from finite samples to unseen examples from the same distribution, but the kinds of things that allow us to say, go to the moon when we've never been to the moon before and get it right the first time, because we are able to extrapolate outside of data based on some mechanistic knowledge or some kind of compositional understanding. And these are kind of orthogonal considerations that at the end of the day, the systems that you build in that world very may well use deep learning or use neural networks for function approximation for whatever purpose that function approximation serves within those systems. And then the debate ends up being, well, do we call that deep learning or do we not call that deep learning? Whatever it is that is neural networks plus, all these things that have nothing to do with, the form of the function.
I think I have a very broad definition of deep learning. So it's the idea.
Comparatively narrow one. Maybe.
Right, although we shifted all the time. But basically, you parameterize a model by connecting modules with each other that are more or less differentiable, that are controlled by parameters, and you train this, optimizing some function, not necessarily minimizing, but optimizing some sort of function using a gradient-based algorithm, right? So that's deep learning in its most general form. Now, you can use this for supervised learning, you can use it for reinforcement learning, you can use it for self-supervised or unsupervised learning, other forms of learning. That's kind of an orthogonal direction. So what we were talking about previously is the limitations of supervised deep learning, okay, which is what 95% of practical applications are using. Reinforcement learning is even more limited in some ways because it requires interaction with the world that is not always possible. So for example, we currently cannot use reinforcement learning to train a car to drive itself. It would require maybe millions of hours of training and probably tens of thousands of fatal accidents before the car learns to drive. So, how is it that humans can learn to drive a car in 20 hours of training without essentially causing accidents for most of us? Clearly, there is something we're missing in the paradigm of learning. So, possibly it's this idea of self-supervised learning, which is one of the tricks that's used in the BERT system that Michael was describing, where there's a prior pre-training phase where you don't train the system to do a particular task, you just train it to sort of understand the regularity in the data. In the case of this, you're training it to fill in the blanks. Show it a sequence of words, take out 15% of the words, and train the system to predict what those 15 words were, fill in the blanks. We know how to do this with language, it works really well. We don't know how to do this with signals that are high dimensional and continuous, like say images. So if I don't give the system a sequence of words, but I give it a sequence of frames from a video, and I take out some of the frames, and I ask the system, can I reconstruct the frames that I took out? This is a very difficult problem that we don't quite know how to solve properly. And it's because, let's say that the frames we take out are the last ones in the sequence. What the system has to do is predict the future, like paint the world in the next few seconds, right? And a lot of different things can happen that you can't really predict. So that creates a technical difficulty, which is solvable for discrete signals like text, but not really for high-dimensional continuous signals. So what that means is that there is a lot of things that we don't know how to do. And that's just for this idea of self-supervised learning. Now, every task, the tasks that we know how to do are tasks that seem to be perception-like. So something that you can compute the answer in a finite number of steps, however many layers you have in your neural net. Surprisingly, you can do this for translation, but anything that will require a chain of reasoning to arrive at a solution, we basically don't know how to do this with deep learning. So we can't. We haven't figured out kind of a neural net architecture, if you want, that would allow a machine to learn logic. Okay, and that's sort of a limitation. And there's big debates with Gary Marcus and others on like how much prior structure do we have to put into machines so that they will be able to learn this. Another thing we don't know how to do with deep learning is, when we train a convolutional net, the convolutional net learns to represent the perceptual world in a hierarchical fashion. We'd like to be able to train machines to learn hierarchical representations of action space. So if I want to, go to New York from here, I don't have a car, I need to go to the train station, take the train, blah, blah, blah. But to go to the train station, I need to get out of this room. To get out of this room, I need to control all my muscles, millisecond by millisecond, so as to not fall and take into account all the local conditions. And so I have to sort of decompose that plan into subplans and then down to muscle controls. Well, we don't know how to learn representations of this, hierarchical representation of this type for actions. And that's kind of an essential thing if you want to do robotics, for example, or even dialogue systems. We don't know how to train systems. That's what Michael was also talking about. We have this paradigm of training set, test set. But if you want to train a dialogue system to interact with people, you basically have to have hundreds of people talking to the system to train it, and that's just too expensive. particularly for reinforcement learning that requires so many interactions that it's impractical. So we can't train dialogue systems. We don't know how to do it. Something that Joël worked on for a big chunk of her career, and there's a whole bunch of people at Facebook working on it. But it's not because we don't know how to do it that we don't work on it. But it's so I mean, the list goes on of things we don't know how to do. Okay.
But I would like to add another axis. So you can ask, what can we do with C++ or Python or any programming language? I think this is the same question as what can we do with deep learning. Deep learning is a framework. It's not a single thing. So if you look at it in this general view, then I think we can do everything with deep learning. But on the other hand, this is not how people view it, and the axis that people are viewing it is what can we do with gradient-based learning or gradient-based automatic learning end-to-end of deep learning. And here, at least my answer is very little. Yes, there are a lot of successes of this approach, but basically it's a brute force approach. And it fails when, as Jan said, when there is hierarchical structure or when there are several stages that needs to be done.
Or when the problem's really simple, right? Or when the problem's really simple, right? Like you take a very deep network and train it to fit a line, and it will learn something that is, like it's no amount of training examples is going to make it exactly fit the line, right? So this is, I remember like a long time ago, so I was involved with an unnamed organization where I had a product that was some like automatic machine learning type tools, and one of the things was, had like just a few basic things, regression, classification, whatever. So there were some mathematicians who saw that there was this open tool API. You upload a data set, it gives you a model, and because they were mathematicians and not machine learning guys, they didn't stick in MNIST or something. They stuck in just a straight line, and it was the model. It wasn't even deep learning. It did some standard machine learning data science stuff. It bins up the data, it creates some features from it, does all this stuff, and the result is it can't fit a line, right? Because and no amount of data is going to make it exactly distill it into some simple algebraic form. So that's we struggle with hard problems and we struggle with really easy ones, maybe.
I had one other dimension to add, which is, given the inspiration for neural networks in some sense came from the brain, as Jan was saying, understanding the implications for the modern engineering results on our understanding of neuroscience and how the brain works, I think is a very interesting question. And I sense many of those connections are not understood. It doesn't feel like the brain can do backpropagation. How the brain forms concepts and assemblies, I think, is fascinating. How it learns using Hebbian learning as opposed to backpropagation. There are intriguing connections. There was a recent paper showing that the sense of smell in the fruit fly can be viewed as sort of randomized features with a very simple network. That's extremely limited, though. The question is how we get hierarchy, how we get convolutions, and so on. I'm curious if Jan has something to add there.
Yeah, I think it's not actually clear that the brain doesn't do backprop. I mean, in the sense that every reasonable learning paradigms that we know about function by optimizing some function, minimizing it, maximizing it, or finding a Nash equilibrium between two functions, right? But it's optimization regardless. To do this efficiently, you'd be crazy not to try to estimate the gradient because everything else is so inefficient. Like zeroth order method where you have a black box function you want to optimize and you're not allowed to, like you're not given the gradient of it, are so inefficient that I can't imagine that the brain would be stupid enough, evolution would be stupid enough to kind of pass that by now. And so if there is an objective function that the brain is minimizing, it would be crazy for it not to use it using some sort of gradient-based algorithm or method. And so the question is, how does it evaluate the gradient? How does it estimate the gradient? And then how does it, update its internal parameters? So, what's funny in the visual cortex, for example, is that you have as many connections going backwards in the visual hierarchy. The computation for everyday recognition of objects seems to be essentially feed-forward. So if you show, you flash a picture in front of someone, or you flash lots of pictures in quick succession, You can measure the time it takes for the signal to basically propagate all the way to the infotemporal cortex where objects are represented, and it's about 100 milliseconds. And if you go through the circuit, it's basically enough time for just a few spikes to get through. There's no time for feedback. There's no time for kind of reasoning. So simple everyday vision is essentially feed-forward. Now, there's actually more connections coming back as they are going forward. Those connections are there for a reason. You know, it could be attention, it could be whatever, but it's probably learning. It probably has to do with learning. May have to do with estimating gradient, with computing prediction errors, with, you know, we don't know what, but there are sort of various hypotheses for this. So, you know, I would actually find it surprising if the brain managed to learn without some sort of gradient estimation. So that, you know, the second thing with the connection with biology is that the standard model in psychophysics for pattern recognition was template matching until recently. And visual neuroscientists didn't actually have a very good computational model of what goes on in the visual cortex until they started using convolutional nets actually as their model. So convolutional nets now are the standard model that neuroscientists use to explain what they observe in the visual cortex. So they take a pre-trained, generally, convolutional net that is not designed to mimic the anatomy at all of the brain, but some sort of standard convolutional net. And then they put a subject in an MRI machine and then try to explain the variance of what they observed in the MRI machine with, you know, the layers in the convolutional net, and then find that, you know, there's going to be one layer where when you try to predict the activity of the brain with the activity of that layer, you get a pretty good prediction. And so you go, you know, in V1, V2, V4, and IT, and there is sort of various levels in the standard, you know, ResNet 18 or whatever that best explain what you observe. And that's the best models we have.
And can I follow up with that? You think, or any of you think, that the kind of problems that are really accessible to deep learning are also the ones where, some sense, human activities, where our own brain has been involved? Because you can think of many tasks where our brain is totally unable to do this. Then, so is there a correlation between these two? Anyone wants to speculate?
I don't want to monopolize the speech here, but we like to think of ourselves as kind of generally intelligent, right? There is this term, artificial general intelligence, which is supposed to be the kind of intelligence that humans have. Humans are incredibly specialized. We're extremely, extremely, extremely specialized. We don't like to admit this, but this is true. I mean, you know, it's just I'm going to use a theoretical argument. You can probably make this argument better than I can. But let's imagine our visual inputs are binary, right? We have about 2 million optical fibers coming into our brain. So there's, you know, 2 to the 2 million to the power 2 million different input configurations that can go into our visual system, assuming it's just binary, which is not. Now, the number of binary functions of one output, of Boolean functions of one output, with 2 to the 2 million inputs is 2 to the 2 to the 2 million, right? Which is insanely large number. Now, among all of those functions, how many of those can our brains actually compute? And it's a tiny, 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 tiny sliver. In that sense, we're incredibly specialized. And it's due to the type of pattern of connections that we have in our brain, where our neurons are only connected to their nearest neighbors, or they're connected with, you know, the neurons that kind of face them in the fold of the cortex. It's all very organized for a particular function, and so that makes us incredibly specialized, which is why we are subject to visual illusions and things like that, and there's tons of tasks. So one thing that we've realized recently with experiments like AlphaGo, so, you know, training basically what amounts to a convolutional net to play Go. There was some idea somehow that the best human Go players were very, very close to God, if you want. So the perfect Go player would you know, give a handicap to the best human players of 2 stones or something like that, or 3 stones, and then and lose. Turns out it's not true. It turns out AlphaGo showed that humans really suck. I mean, they really suck at Go. We're just not very good at it, you know, compared to, I mean, those machines are, you know, can beat the best humans with like 9 stones or something handicap, which is insane. So it's very humiliating, but it shows that, I mean, Go was designed to be actually difficult for humans. Like, we don't have enough short-term memory to remember the, you know, all the possibilities in a tree of possibilities, and we don't have enough compute power to do this quickly. Computers are much better at this.
Yeah. Yes.
Will it be helpful to have a catalog of the 10 most foundational problems in deep learning that need attention, or the 10 most fundamental tasks? I'm asking this is because it has been a fascinating day, so thank you so much. But at the end of the day, I wanted to make a summary, to take something home. And there are so many things that you guys have mentioned, very fascinating things. I cannot produce such a summary.
I guess the question
10
is...
foundational problems in machine learning or deep learning, and 10 foundational tasks that you would like to be resolved within the next X years.
But by foundational, you mean mathematical understanding?
Yes.
I guess the question is a kind of a Hilbert, we'll set a list of Hilbert's problems.
So why 10? Let's focus on 2.
You can choose your own number.
2.
So I will talk about 2. One of them is that we do not understand the inductive bias of deep learning. This means that if you take let's go back to what I talked in my talk about learning the multiplication board. Now, if I show you just 50 entries, 50 random entries for the multiplication board, there are many ways to fill the missing entries, right? Any of them is as good as any other. Without prior knowledge, there is no way to choose one over another, okay? Now, what we do in machine learning, we say that there is no free lunch, so you need to have some prior knowledge or some inductive bias in order to prefer one filling of the missing entries over another. You can think about it like defining an order over models and in advance, and you want to choose a simpler model following Occam principle of finding simpler problems. So this is what we call inductive bias. Now, question number 1, we do not understand what is the inductive bias of deep networks. Okay? Now, question number 2, in practice, gradient-based algorithms work very nice on some problems. In theory, we know for sure that they cannot work for most of the problems. We can prove it, okay? So what makes practical problems so special that gradient-based algorithms work for them? So understanding what are the properties of real-world data sets that enable efficient optimization by gradient-based algorithms is question number 2.
But doesn't Django et al. Show that actually it works even with random data? So there's nothing to do with the generalization depends on the properties of data, but like optimization doesn't.
So also in optimization, maybe you can overfit random data.
That's what I'm saying, the generalization.
So making optimization, so what you're saying is that not just optimization of the training set by generalization. This is what PAC learning means by optimization, but it's a good comment. Okay, so I will maybe rephrase what Sanjeev says. Optimizing just for the training data, just for the data that you see, assuming that you have a big enough network or big number of knobs is easy, and this is known how to do this. The question is how to do optimization that will generalize also to unseen examples. This is what I mean by how gradient-based algorithms succeed on unseen examples.
Is there any candidate for a third problem to add to that list?
So we're able to recognize objects and images really easily, and if you came out with a new camera tomorrow that had a slightly different compression algorithm or a slightly different filter, none of us are worried that we would suddenly lose our ability to recognize objects in the images. But models that we have today are extremely sensitive to what to us would seem like perceptually minor shifts in distribution. And we know of a couple like kinds of classes of invariances we'd like our models to be robust to. I mean, convolutional neural networks are, the deep insight is partly based on one of these, that like there should be translation invariance in the feature learning. But in general, like this is just one among many sets of kinds of invariances that we have that allow us to sort of behave reasonably in new situations. And we sort of don't know what the other ones are. Like you can come up with many ways of perturbing a data set that aren't just small shifts or random zooms, where everyone, many ways of distorting the data such that everyone would still be able to recognize all the objects. And identifying a kind of broader set of invariances that models should respect, and identifying the algorithms that can actually be robust to these kinds of shifts in distribution, I think is a fundamental challenge to using machine learning outside in the world where the test data never actually comes from the exact same distribution as the training data.
Yeah, so to formulate another question, I think, so there's the issue of the distribution shift that maybe you train on images that are different from what you'll be tested on. I think the more salient property of intelligence seems to be, and this came up when you said earlier about going to the moon, that what we train on is not even the task that we are tested on. And there all hell breaks loose in terms of theory. And that's, I think, a very nice question. And I think there are ways to start approaching it. Watch for a paper of ours in a few days. But yeah, but I think it's just the first step.
Michael, you have something to add to that?
Gosh, this is interesting. I think, again, coming back to the brain, trying to reason about how the brain is representing concepts and relations and memory. And sorry, this is a little bit ill-formed, but I think somehow understanding the capacity of the representations that neural methods are currently producing. And if you think about the language work I was talking about, we typically represent things in fairly low-dimensional, dense spaces, like word embeddings are a few hundred dimensions. Number of neurons is maybe a few hundred, few thousand at most. If you think about the brain, it seemingly has a rather different architecture where you have, I think, high-dimensional vectors which use sparsity at a great effect. And for me, understanding how the capacity of those two alternatives plays a role in memory and reasoning and so on, I think is very important. And in some sense, we've ended up with low-dimensional dense representations because the architectures we work with, like GPUs and so on, tend to be very amenable to that kind of space. But investigating architectures where you have 10 million neurons, of which 1,000 are firing at any time, and reasoning about the theoretical properties of that space, I think would be very interesting.
So we take another question from the audience?
I have one here.
Yeah.
Thank you. Thanks for the wonderful day. So I think it's been a great conversation around the reinforced learning especially. Now, that's great, especially in the context of building out models focused on certain domains, certain use cases, and strengthening them as we go. Now, one of the strengths of humans also is that while we are specialized learners, Jan, to your point, but we are also, at least for now, pretty good at drawing inferences from our cross-functional experiences too, or across domains as well. We can call that wisdom, common sense, intuition, whatever be the case. So what comments would you have, the panel, about the research in the direction of the transfer learning or the inference-based learning as well, such that each time we're talking of creating models, we're talking of availability of the training data and the time, and it's a sweatful work ultimately to train the whole thing. Now, different models can need different levels of sophistication, but how about accelerating the process of deep learning across functional areas through thinking about transfer learning-based concepts, and in a way, therefore, opening up the idea of a hyperdata to more domains, more areas. So, inference-based and transfer learning.
So transfer learning is really a matter of routine now in large-scale production. So the systems, the image recognition systems, for example, that are used by Facebook, when users upload something between 2 and 3 billion photos on Facebook every day, every single one of them goes through a handful of convolutional nets that do various content filtering and tagging and whatever. And there is sort of a main trunk, if you want, a main convnet. That one is trained through transfer learning. So it's first trained with something like 3 or 4 billion images, not to classify them into hand-provided labels, but to predict hashtags that people have typed when they posted them on Instagram. Okay, so get 4 billion images from Instagram, which is a couple days worth. Then make a list of the 17,000 or so most frequent hashtags that people type, and then train a convnet to predict which of the 17,000 hashtags are present for every image using those 3 or 4 billion images. Then chop off the last layer of that convnet and train a couple layers for whatever task you want. With this protocol, you basically beat the record on ImageNet, Pascal, basically all the standard computer vision data sets. So that's a matter of routine, okay? Only for vision. For text, the routine is more the self-supervised pre-training, where the BERT style. I mean, it's not really routine because BERT is like ridiculously expensive computationally, so to use this in production is actually kind of a pain, but it's Word2Vec, for example, is completely routine.
You could add that as like to your grand challenges is explaining like the current mode of transfer learning is always you train for one task, you take those weights as the initialization, chop off the last layer, add a new one, initialize it randomly, and start training from there. And this makes the world of difference. And I think if this had like some solid theory backing it, people would have, treated this like this was the biggest thing since maybe like the breakthroughs of 2012. And I think it's just the fact that it sort of seems like no one has, I think, to my knowledge, even the faintest idea of why, of how to explain just how dramatic the effect of this initialization is. And
thanks. I was wondering if you think on a sort of a 10-year timescale and real-world applications of deep learning, what you will worry about?
In terms of societal impact?
Well, I think incompetent people kind of misusing it, not necessarily for a nefarious purpose, but just, creating bad situations through incompetence. And this can happen in several ways. So, for example, if you want to train a face recognizer, right? So Facebook has face recognizers, Google too. And you collect a representative sample of the American population. You train your convnet on these samples. It's not going to work very well for black people because they represent 10% of the population. The neural net, can minimize its objective function quite well by completely ignoring them and just working on sort of brighter skin tone. It's also easier for it to work on brighter skin tone because there's more contrast, right? So there's more amplitude and variation in the pixels, and so by default, it's just not going to work as well. So it's easy to fix. What you do is you equalize the frequency of different categories of people to make sure that everything works more or less to the same level for everyone. But the thing is that you have to know that in advance, otherwise you're going to make a lot of people very upset. And you have to have an objective way of testing as to whether your system is biased or not, according to categories that are well established. There's probably a lot of biases of this type that you don't even realize you're making. So there's quite a lot of work, in fact, on sort of trying to figure out really what this means, how you measure bias, how you suppress it. So bias, there's been a lot of talks in the media about AI systems are only going to work for white males because all the people working on AI research are white males. The bias is not in the kind of the models that we build; it's in the data, and so it all depends on how you collect, process, equalize the data. The models themselves they don't have that kind of bias in them. But these are important questions, and there is fairly large teams in all of the major companies that I know of that work on this, and they even got together I was instrumental in doing this and forming something called the Partnership on AI, which is basically a forum for everyone to discuss those issues in the open, because it's not something each company wants to solve independently. That's something you need to discuss in the open. So that's one thing. Second thing is, if we're going to deploy self-driving cars, if we want people to trust it, it's going to have to be like clinical trials for drugs, in the sense that the testing process has to be sort of open and government mandated, or mandated by a company you can trust. Like airplane parts are tested by Veritas or whatever, one of those companies that kind of put a seal of approval on it. So you need an open testing process, because you're not going to be able to prove that your system works with equations or with anything else than thorough testing. And so the testing is where it comes down to. A lot of people have been saying, machine learning system, deep learning system are opaque. We can only really understand how they work. Therefore, we can't use them for anything life critical. And that's just not true. We've been doing this for decades with medicine. A lot of medicine we take, we have no idea how they work. But they've been thoroughly tested, and they work. So that's all we need to do with machine learning system as well.
I partly agree. I agree that the emphasis placed on the opacity issue is kind of misses the point usually. I think the big issue, though, that is just the elephant in the room is if you have a task like recognizing faces, like your task is explicitly to do recognition, to do perception, to make correct inferences. That's great. You build a system that gets high accuracy, that's wonderful. But if you listen to people talking about how they use machine learning, your next doctor is going to be an AI, we're going to curate the news with AI, we're going to generate the news with AI. You hear the kind of talk about what AI is going to do, and then if you try to match that up against a prediction problem, you realize it's not a prediction problem. Like the vast majority of things that we do in the course of like economic life, most of the things that we do are not simply estimating correlations and then plugging them into some kind of decision rule. And I think what happens is that machine learning it vastly broadens the set of like things we can automate, but we can only automate those things where we can somehow cast it as a prediction problem and then come up with some short hop of like little steps that we could take to go from our prediction to the decision that we make. And when a problem is not a prediction problem, but you try to drive it with the results of a predictive model, this can kind of create a whole ecosystem of like horrible effects. So what we ultimately want is policies that say what we should do. So yeah, if you want to tag people's faces, recognize users of Facebook and photographs, I think prediction is the right tool. But when you make a lending decision, for example, people say, well, let's collect big data, we'll train a model, figure out who defaults. There's lots of things that might be associated with who defaults that are not things that should be driving your decision. And the reason why is, like for example, if you looked at someone's footwear and you found that this was a useful feature for predicting whether or not they defaulted on a loan, it doesn't mean that this is a reasonable way to operate as a bank to make decisions based on people's shoes. Although I would grant Sanjeev a loan today, those stylish boots. But the reason why it's not the right way to make a decision is partly, for starters, is that actually you're not just making a prediction, you're participating in a complex system of incentives. And among other things, your purpose isn't to go out and tell people to intervene and wear different shoes, and then you'll grant them a loan, right? So you have all these systems that are engaging in the world in a very naive way. They're making predictions, it's driving decisions, and these decisions are not just giving us accuracy. Like accuracy isn't the objective. They're actually setting a set of incentives that are distorting the behavior of, when you do it at the scale of a large corporation, millions or billions of people who are changing their behavior. So like, I've been trying to work on up this angle. I haven't figured out exactly how to articulate it, but I think like autocorrect is like somehow this clear example of this naively applied predictive technology that actually has this absolutely horrible effect. Like everyone I know who has like a non-common name, like I was hired as part of a job search that was run by someone named Param. And every time I wrote an email to him, it was autocorrected to parameters. And maybe they had some prior knowledge about my field. But the fact that like what name someone assigns to their child might now get influenced by the fact that every single sort of text-based communication, which is increasingly, the lion's share of our communication is mediated by a predictive tool that is sort of telling you what you meant to say and is making these like disparate kind of errors from common words or from rare words to common words. So I think this is the problem, is that we sort of will only solve, I think the biggest risk isn't that we will have the AGI and then we have to worry about what will the superintelligence want to do. I think the biggest risk is that we have this sort of good predictions and we don't crack the greater problems beyond that, and we have people coming up with ways of sort of applying the wrong tools to the wrong problems at scale, and we don't have any kind of coherent policies or way of thinking about how to sort of mediate the fallout from that.
Here you go. Here's a mic.
So a lot of deep learning is based on minimizing a loss function. And my question is, what is known about the geometry of that loss function? And is this a productive direction, or is there a reason that this is not?
Naturally, it came to me. So we already discussed it a little bit. I think that this is a less productive direction because we know for a fact that there are loss functions which are bad geometry, whatever you want to define bad. For example, bad local minima. Yet, for these loss functions, the specific initialization and specific algorithm finds good solutions in some cases. So maybe you should be more careful about defining what exactly you are looking for.
But maybe also what is known.
Well, not enough, that's for sure. But certainly the fact that, as I was mentioning at the end of the talk during the question session, you need to make the networks much bigger than necessary to learn the task, which statistically speaking is an abomination because now you have an over-parameterized model. But it just turns out that if it's a multilayer neural net, it's not going to overfit for some reason. We don't understand why. What we know is that the solution space are very degenerate. You know this too. When you find a solution, there is lots and lots of dimensions where the objective function basically is flat, and then a few directions where it goes up. And the number of directions where it goes up is probably related to the difficulty of the complexity of the task, probably not so much with the architecture. So, I mean, there are intuitions like this that there is some experimental evidence for them, not super great theory. And, I think our intuitions in the past have proven wrong. So one big reason why people stayed away from neural nets is that there was this belief that somehow, because it was non-convex, it was very difficult to optimize. And I think the one story we can tell is like, this famous beginning of is Anna Karenina, or all happy couples are the same and all unhappy couples are unhappy in a different way, right? So all convex functions are the same, but all non-convex functions are non-convex in a different way. And neural net non-convex functions appear to be well behaved somehow in such a way that we can minimize them. Now, I think if we changed some very simple characteristics of what we put in our neural net, it would make them completely intractable. So for example, if instead of a ReLU or a sigmoid or something like this in a neural net, you put a non-monotonic function, a function that goes up and down, all of a sudden, I think learning doesn't work anymore. You have tons of local minima, things don't move, you get stuck, you have plateaus, right? So those choices are not innocent. Perhaps the best practical progress of neural nets over the last 10 years is to have replaced sigmoid functions, sigmoid nonlinearities by ReLUs. The advantage of ReLUs being that they're scale invariant. You can multiply the input by 2, the output gets multiplied by 2, but otherwise it doesn't change. Whereas with a sigmoid, there is kind of a scale that needs to be picked. And so using ReLUs allowed us to train networks with 50 layers, which we couldn't do with sigmoids. So yeah, I mean, there are very simple things like this that we don't even understand.
So is there any theorem that's like the loss landscape when you use sigmoid has this bad property, but when you use ReLU it has this better property?
No.
But
I was going to say, I'm going around giving a talk where I say, don't think about the landscape, think about the trajectory. And it seems that, that most of the landscape, the algorithm would never encounter. So it only encounters the part of the landscape that's along the trajectory of gradient descent. And in the last year, there are now papers which are leveraging that by several groups, including ours.
But thinking about generalization theorems based on Pack-Bayes or Sanjeev, your recent work on compression, I think there is evidence that if the final point you reach is relatively robust, so if there's a large volume around that point such that the training error doesn't change much, that is one way to guarantee.
It's probabilistic robustness, not all directions, yeah.
Yeah, there's a, but that gives you guarantees in terms of generalization.
It's a property of gradient descent that it finds those networks, I think. Yeah, it seems.
I mean,
stochastic
who knows
gradient descent.
why we find it, but at least you can say something about the geometry of your endpoint and how that relates to generalization.
So, thinking about going back to the theme of alchemy in science, so just want to bring it back there. So clearly, at some point, what we did in science, discover kind of certain laws of nature, which I guess is more these kind of organizing principles. So, is there any way in which you can envision that kind of structure appears out of deep learning? Which would be finding, I guess, your multiplication table, for instance.
It's not clear to me it's going to resolve the multiplication table issue. I mean, it's also hard for humans to figure this out, right? Humanity figured out multiplications relatively recently in the history of humanity, only in the last, 3,000 years or so, maybe 4. And it's still very hard for kids to learn the tables, right? It's not like there is any kind of regularity in it that you can learn it other than by, rote memorization. So that problem might be completely hopeless. Yeah, no, I think there could be some sort of theory, perhaps beyond the classic sort of VC theory of generalization, that would be sort of a, kind of a theory of intelligence and learning. I don't know what form it would take. Maybe there isn't any, but something that would explain, simultaneously how, some principle that would explain how humans learn and how animals learn, and would apply to machines as well. Maybe some sort of principle of least action kind of thing. I don't know if there's something we can come up with, or maximum entropy. I don't like those things because there's kind of statistical quantities that we can't measure. But there could be something like this that would be sort of a guiding principle. Possibly.
I guess we were discussing this the other day around here that, would it I guess at dinner, that, if Newton, instead of Newton, we had a computer looking at the same data, Copernicus and so on, would he discover the inverse square law or, inverse 2.001? And there's a big difference between the two.
Any other speculations on this?
Well, the inverse 2.002 perhaps doesn't conserve energy or something, right? So, yes. so there's maybe some other characteristics of that theory that would kind of invalidate it. Yeah, I mean, I'd like to know what form such a theory could take. But it could be also applying equally well to evolution. So what is the process by which that drives evolution? Right. I mean, it's a question also for physicists, right? That the second law of thermodynamics is kind of locally violated by life. Not globally, of course, but kind of locally. Maybe there is something to kind of look for here in the sort of principle of self-organization, and it's questions actually that the people in cybernetics in the 50s were really worried about. They were thinking about those questions. We don't tend to think about those anymore.
Maybe just I will add that once deep networks will solve artificial general intelligence, they will also tell us how they do this.
There are so many fascinating things going on in this in this business with where progress is on an immediate timescale. So I hate to ask a speculative question about a hopefully much longer timescale. But since no one has brought it up, I might as well ask the existential question of relevance to theoretical physicists and mathematicians and other people of our ilk, which is the obvious question of when the machines will replace theoretical physicists and mathematicians. And we can sit around and have all the usual discussions about the ineffable greatness of human creativity, blah, blah, blah. But, I go back and forth about whether there's something really to that. But I guess the practical version of my question, and it was partially triggered because since you mentioned going back to the 50s, there are things like this going back to people like Marvin Minsky, other people in the 80s. But I'm wondering whether there's an update on a combination of machine learning and automated theorem proving, for example. We can come up with, I don't know, millions, probably, certainly tens of thousands, hundreds of thousands, maybe millions of interesting, non-trivial mathematical statements phrased in first-order predicate logic, and do that. So you give lots and lots of true theorems. Can machine learning learn how to prove theorems from large data sets like that? And again, I know this is the sort of thing that was talked about already in the 80s, and there's an obvious combinatorial explosion back then. But I'm asking, given all the things happening now, is there even it's not a practical question yet, but is there any subset of this, of your community who's thinking about this question?
So about theorem provers, this is not a particularly hot topic anymore, except for a particular set of applications called formal methods, which is kind of proving that programs are correct. So you write a piece of program that's going to control an airliner. You run it through this thing, and it's going to tell you, this program is not going to crash, right? Or at least not because of all those errors that we envisioned. So that's what theorem provers are used for now. They're not actually used to prove like real theorems, because most of when you use the theorem prover to generate theorems, it may generate tens of thousands or hundreds of thousands of true statements that are completely uninteresting, most of them. Like there's only a small number of theorems that actually are interesting. And then the theorems is only half the story, right? It's more like, what's the mathematical construct that you're going to work on? And how are you going to get the understanding of this by just manipulating symbols? It's not clear.
There's been various stunts I've seen. I mean, I think of them as stunts. Stunts that I've seen recently where people say, you feed in, blocks and inclined planes and stuff like that moving around, and the machines discover the law of conservation of energy. But it's because you're asking them to look for things that are made out of positions of velocity and so on.
Yeah.
That's 99.999% of the challenge. So that's why
Exactly.
I'm talking about something, the issue of theorems is a little bit cleaner. And I can tell you that if tomorrow you told me that without cheating, knowing roughly what a kid in grade 8 knows, a computer could prove that E is irrational, I might be tempted to just go to the beach on the next day after that.
Just for one day or forever?
I'd still like to know the answer, but I'd be pretty convinced that would be
Okay. So, referring to your very first question, there's a lot of things that computers can do for us now that mathematicians used to build careers around, like computing logarithm tables or things like that, right? Which we don't need to do anymore. Or even it used to be something that you really had to struggle with to learn to compute integrals, and now Mathematica does this for you, pretty much, more or less. I mean, if you're a powerful enough computer, it will just do it. And so, yeah, I mean, there are certain integrals that you won't do. Yeah, that's for sure. So, I mean, there are problems like this, I guess, that you sort of delegate to a machine that can do it for you, and that the level of things that we're going to be able to delegate to machine is going to kind of go up and up. But for quite a long time, I think we're still going to have humans driving the process. It will just make every human more powerful, essentially, by having basically interacting with a colleague. Like I mean, we all have colleagues. I don't know about you, but being the head of a research lab and as a consequence being the stupidest person in the lab, almost everybody else is smarter. There's people in the lab who are like incredibly good problem solvers, right? If you can formulate a problem, you go see them and you get a solution, in minutes, hours, or days, but pretty quickly. Perhaps a computer will use computers like we use those colleagues, basically, right? And soon enough they'll probably find, in a couple of centuries, they may find their own interesting problems to work on. Whether those would be interesting to us is not clear, but that will be their screensaver.
Can I say something? Yeah, sorry to break the news to you, Jan. Actually, your competitors, other companies, they are people working on theorem proving. I guess I'm not sure if I could name names, but we can talk privately. And it's in domains like, as you would imagine, Euclidean geometry or elementary number theory. And the idea is that, yes, you have this long tree of possible proofs, but you're going to have some kind of a trained procedure that sees a lot of examples and comes up with proof strategies, like let's use induction and what's a suitable induction. So people are trying to do that. It's not clear where it'll go, but definitely. Does that ring a bell?
I agree. Yeah.
Yeah, there are people trying to do this.
Yeah, I know about this work. Yeah.
Like an existing system? Oh, that's very different. So that's very different. So that's what Jan said is logical theorem proving. And that's actually developed to some extent, but it doesn't seem to be up to the task. This would be learned theorem proving. So you see examples, and it helps you come up with strategies. That's the idea, as I understand. But there are no examples you can point to. No working systems that I am aware of, yeah. Okay, so maybe we'll stop here. It's 6:30. Let's thank all our panelists again for coming out here.